Real plants never run at steady state. From an operator changing controller set points, to variations in the feed, to heavy rain affecting the heat transfer from a distillation column, there are always disturbances. To account for these disturbances, we set up controllers to automatically correct for process changes. The controller will try to force certain variables, called controlled variables, to a set point that is given to the controller. There are a few possible responses of a process when you introduce an instantaneous bounded change to its input, called a step change. The first possible response is that it could approach the new steady-state value. This approach could either be asymptotic or an oscillation that decays towards the new steady state. These are characteristics of a stable process. The process variable could also start moving in an unbounded fashion. A runaway reaction is an example of this. This response is characteristic of an unstable process. A properly tuned controller can stabilize an unstable process, but a poorly tuned controller can even make a stable process unstable. So setting valid controller parameters for your process is crucial. A simple form of control would look at where we want a process variable to be, the set point, and compare this value to the actual value of the process variable. We would compute the difference between these two values, called the error, and offset the manipulated variable from its steady-state value by a multiple of the error. The factor that multiplies the error is called the proportional gain, or KC. This simple controller is called a proportional controller. It works, but it has some drawbacks. It can be shown that this form of controller will have an offset from the set point. We can shrink the offset by increasing KC, but if KC gets too large, the system will become unstable. We can do better. Let's add integral action to the controller. In addition to the proportional control, let's also integrate the error, multiply it by a constant, and add this to the output of the controller. This new controller, a PI controller, has eliminated the offset, but it will overshoot the set point and can increase the natural period of oscillation of the process. Integral action can also slow down the controller's response because the integrated error term takes time to build up. A term that looks at the derivative of the error can be added to the controller to speed up the controller's response and dampen oscillations. This is particularly beneficial to processes that have a slow response time. Derivative action must be used carefully. If there is noise in the input to the controller or other small spikes in the input variable, the derivative term can get very large. The input must be filtered before being passed to derivative control. The processes that we are working with have relatively fast response times, so we will not be using derivative control. By convention, the integral and derivative terms are also multiplied by the KC term. The integral term is divided by the integral time, Ti, and the derivative term is multiplied by the derivative time, Td. A larger integral time will decrease the integral action. A larger derivative time will increase the derivative action. Controllers can be either direct acting or reverse acting. A direct acting controller will increase the manipulated variable when the controlled process variable goes above the set point. A reverse acting controller will do the opposite. It will decrease the value of the manipulated variable when the process variable gets too high. If we have a tank with a level controller on the liquid output valve, we want the controller to open the valve when the liquid level in the tank gets too high. This is a direct acting controller. Let's say we want to use steam to heat a liquid stream. We will have a temperature sensor at the outlet of the heat exchanger and a control valve controlling the steam flow rate. If the temperature of the liquid stream gets too hot, we want to feed less steam to our heat exchanger, so we will use a reverse acting controller.